Welcome to my YouTube channel. Today we'll be looking at an RStudio example that centers on comparing means with known standard deviation. I would read out the problem and we would go ahead and solve the problem using R. So it's a typical hypothesis testing problem where you have two populations. And in this case, the population standard deviation is known. So the problem says, as part of a study to evaluate differences in teaching quality between two statistics course sections, an examination is given to individuals who are enrolled in the course. The difference between the mean examination scores is used to assess quality differences between the sections. The examination score standard deviation from previous sections are sigma 1 equals to 21 and sigma 2 is 410. We're given the level of significance as 0.05, and then we're asked to see if the data suggests a significance difference between the population means and the two statistics sections. So for the data, I would ask that you go to my GitHub page, right? This is the link up here in the address bar. Just type out this link into your web browser and download the data by clicking on this button here, and you download the raw data from my GitHub page, right? So I would also include the link as I type up the code here in R, so you can just copy it from there and paste it on your web browser and get quick access to the data. I would also include the data link on the YouTube video. So just in case you're not able to download it from you're not able to see the link on the website, or you don't want to type out the link from the RStudio, I would also put it on the YouTube description page. So you can just click on it there and it will take you directly to the GitHub page that has that data in it. All right, so let's go ahead and start. Okay, so the first thing we want to do is to state the null and alternate hypothesis for the problem that we're working with, right? And we want to state what mu1 and mu2 is. So we see that we have two stats, course sections, right? So basically the exam is administered to the students enrolled in those two sections. So we would have our mu1 as mean exam score let's just say for students. And then mu2 so that's what mu2 would be. And then our null and alternate our null hypothesis, and then the alternate hypothesis, right? So here it says, do these data suggest a significant difference between the population means at the two statistics sections, right? So that means for the alternate, what we're looking at is that mu1 minus mu2 is not equal to 0, right? Which is a hypothesized mean, right? is the mean exam score for mu1 equal to that of mu2. So that's what the alternate is saying. And then the null would be that mu1 minus mu2 is equal to 0. So this is how you set up your null and alternate hypothesis. So the next thing we want to do is to install some libraries, right? And then load those libraries, because that's how we would be able to import the data that we have or the data that we've downloaded into R. So let's go ahead and do that. So you can either call them R libraries or R packages. So install packages, just click the first one. So basically the read Excel package allows us to import Excel files into R. And then you want to load the package. All right, so you can click on the run button up here to run each of the line of code, right? So if I click on it, all right, so it has installed it, right? It has installed the package there. And then the next one, to run the library, we click on run. So we've loaded that library called read Excel, right? So that's how you do that. So the next thing now is to import the data into R. So as I promised you earlier, I'm going to include the link here so you can download it. All right, so that's the link to the data. So if you can just copy everything out here and paste it in your, copy everything into your web browser, and you can download the Excel file from there. So the read underscore Excel function helps us to import Excel files into R. So I would run this. All right, so I have my data in there already, right? So you can see if you click on the global environment, right? If you click on it, it shows you how the data set looks like. So we have two sections. So the first section has 41 students in it, right? And you can see the exam scores for those 41 students. And then the second section has only 16 students. But then what you would notice is that because they are not the same length, right? 41, 41, we have a lot of NAs, right? So R sees it as missing values. So we would have to clean this data in order to take out the missing, or just to delete these rows that are basically missing or that doesn't have any information in it. So that was section 2. So I'm just going to name my new section as section 2, right? And I would say we use the function na-omit to delete rows that don't have any information from our data. So we just call the data, because data, that's how we store our data, right? And you use this $sign to select specific columns within that data. So when you click the $sign, then you click on section 2, right? So we run that, and you can see it now, right? We have that new values here for section 2, and it has only 16 rows. So basically all that NAs has been removed from section 2. So now let's go ahead and state the parameters, right? Our first parameter is alpha, which the question gives to us as 0.05, right? So you can see it here, significance level, 0.05. Our next parameter would be for us to count the number of rows that we have, because that's our sample size, right? N1 is the sample size. So I'll just say length allows us to count the number of rows we have, then data dollar. So that's section 1, right? So this here would give us the number of samples we have in section 1. So if I run that, you can see it up here. We have 41 rows, right? So our sample size for the first section is 41. So I can just write here 41 samples. And then we'll do the same thing for N2, which is sample size 2, length, right? But this time, we're not calling section 2 that is inside data, because remember, we already created a new section 2 here, right? So we're just going to use that one. So you would say section 2 here, which is the one that is cleaned, right? Result, and if we run that, we have it as 16 rows, right? So we have 16 samples in section 2. So that's how you do that. The next thing is to calculate the sample mean. So sample mean, I'm representing that as SM1, right? So let's say, let me just put this as a sample size, so you can know what we're doing there. And then this would be sample mean, right? So we use the function mean, and then open bracket. Remember, we need to call this, and then I just like to put the result by the side so you know what the result would look like. So if I run that, my sample mean is 80.26. So 80.26 for sample mean 1. And then for sample mean 2, remember we use section 2. So when we run this, it's 83.81. So basically, the sample mean for the second section is higher than the sample mean for the first section. But you have to note that in the first section, we have 41 students compared to the second section where we have only 16 students. So that's an important thing for you to note. And then the next thing is for us to put our standard deviation. We have 2 standard deviations, sigma 1 and sigma 2, right? And the question provides that because it's based off historical information, right? So you can see it here. The first section is 21, the second section is 14, right? So all we just do is write 21 and 14 here. So I'm just, so that you know where that value is coming from. Given population standard deviation for first section. All right, so you know where that is coming from. We're not manufacturing it or anything. It's from the historical records. Now, the next thing we want to do is compute the standard error. Because the standard error is basically the denominator of our Z statistics, right? So the equation is the square root of sample mean 1 subtracted from sample mean 2. Sorry. Sigma 1 raised to the power 2 divided by n1. That's the equation, and then sigma square root of 2 divided by n2. Right, that's the equation for standard error. Apologize for the error, my part. And then we'll just call this back here. Right, and just put the result so you can see it beside it. Right, so we run this, right? So sigma 1 is basically 21, and we take the square of it, and then divided by n1, which we already have it up here, line number 25, and we do the same thing. All right, so I'm just going to say deviation and deviation here, so you know what that means. All right, so let's run this. Oh, see, so now here is where you start getting an error. If you don't run the previous line, right, you would get an error, because in this case I forgot to run line number 33 and 34, and R is telling me, hey, there's nothing like sigma 1, right? So I have to run line number 33 and 34, right? So now if I run, oh, okay, so I made a mistake as well. So those are the little things that you need to pay attention to as you run your code, right? So I did not put this properly. It's supposed to be sigma 2, but I only put sigma, right? So R gives me another error. But now if I run it, I'm not getting any error again, right? So my standard error is 4.79, which I can approximate to 4.80, right? That's my standard error. So now we can compute the test statistics. So because the population standard deviation is known, in this scenario, we use the z-test statistics. So it's going to say z underscore test. And then the equation for that is actually sample mean 1 minus sample mean 2 divided by the standard error, right? So all right, so let's run this. So we have it's negative 0.74, right? That's our z calculated value. And then we have to compute the p-value. So a p-value equation would be 2 multiplied by p-norm bracket z test. So in this case, we're not subtracting 1 from it because our z value was a negative, right? So we're going to use this negative z distribution table. So that's why the lower tail, you put that as true. If it was a positive number, if our z-test was a positive number, then you would put the lower tail as false, right? So please take note of that. Sometimes that can be very confusing to people. So if this value here is positive, right, change this to false. But because it's negative, you leave this as a true, right? Please take note of that. And then the reason why we're using 2 here is because we're working with a two-tailed, right? It says not equal to, we're working with two-tailed. So that's why we're using 2 here. So I'm going to run this, and then you can see what our p-value is, which is 0.46, right? Now, we look at the criteria, which is reject HO if P value is less than or equal to alpha. So I'm just going to write an if else function. If P value less than or equal to alpha. If else, then not reject. Yeah. Okay, so from this. Okay, so I'm just going to run alpha again. For some reason, she's not seeing what the alpha is. All right, so here is your final stuff. Do not reject, right? That's because 0.46 is greater than 0.05, right? That's why it says do not reject. So when we say do not reject, that means if we come back to our hypothesis here, right, that means this is true, right? And this one is false. So basically mu1 is actually equal to mu2, right? So we can have, I also like to put like an interpretation, right, of what that means, which is the sample results do not provide sufficient evidence to conclude the statistics sections differ in quality, right? So basically the education quality in the two start class sections are basically the same, right? That's what that is telling us. So please, I hope this was helpful to you. So you learn how to import data into R and also learn how to do hypothesis testing when the standard deviation is known. Please like our channel if you find it helpful and also subscribe. Thank you for watching.